from Canada, but now in Taiwan. He used to be a professor at McGill for many, many years, but now he got a position in Taiwan. And I'm very pleased to have him in Korea. We'll talk about Erdős-Sós Conjecture, please.
Thanks, Angel. I'm very pleased to be here. I want to tell you about some variants of the Erdős-Sós Conjecture made by Paul Erdős and Vera Sós. Vera passed away this year, unfortunately. What to say? So let me start off talking about the Turan number, just to put this in context. So this is a pretty basic question. The Turan number, x and h, is a maximum number of edges that you can have in a graph with n vertices that doesn't contain h as a subgraph. Right, and this was first studied by Mantel in 1907 for H the triangle. Right? And when H is a triangle, what's the best thing you can do? Well, you make a complete bipartite graph with the parts equal as possible. Right? And then Turan went on and did this for a clique with 4 vertices. Right? Then you have a tripartite graph. Right? And you can partition a clique into 3 stable sets. And in general for KR,
Maybe you have to.
yeah, I need to be a little bit.
There's some other software has popped up.
Not sure why it's.
Can you? Yeah. Can you
It
just,
doesn't seem to be.
I think you just press the button.
It's not.
Yeah. Yeah.
Okay. I just press that. Okay.
No. Now it should work.
Now it should work. Okay. So in general, you're going to break the. If you don't. Cannot have KR, the most edges you can have is to break it into R minus 1 stable sets with all edges between the pieces. Right? And that's also, if you're trying to put any graph which doesn't have an R minus 1 coloring, then again, if you partition the graph into R minus 1 stable sets, you're not going to have H. So that's a lower bound. And in 1946, Erdős and Stone proved that that was the right answer up to a little O of 1 factor. Okay? And as reported on the Wikipedia page about this theorem, Bolyvás in his text said this was the fundamental theorem of extremal graph theory. Why is that wrong, Sangil?
I don't know.
Because the Jeju workshop was not about vertex subgraphs. We'll come back to this. So let me tell you a little bit. So this is for non-bipartite graphs, right? That doesn't work for bipartite graphs. Let me try to explain to you how the proof of this very important theorem, even if it's not the fundamental theorem, very important theorem goes. Okay? And I don't know how many of you are familiar with Summeretti's regularity lemma. It's a very important result. Basically the result for which you won the Abel Prize, I'd say. Fundamental in both number theory and graph theory. And let me just try and tell you a little bit of what it says. So it's a theorem about taking a graph and splitting it up into some constant p of equal parts up to plus minus 1. Right? And you don't know how much time I spent making sure these parts were all exactly the same size. But and the point is that most of these pairs of parts are well behaved. Okay, so only a small epsilon proportion are not well behaved, which is called regular. Okay, and then the theorem says something, the lemma says something about the parts that are regular, but they have to have positive density. This is a theorem about dense graphs. Okay, so if you don't have epsilon A times B edges between the parts A and B, then it doesn't tell you anything. What it talks about is if you've got a positive density regular pair, then it's what's called quasi-random. It kind of looks like a random graph. The codegree conditions, the number of vertices that two neighbors that two vertices have in common, it looks like a random graph. And that allows you to do a lot of things. Okay? And I won't say anything more precise than that. Okay? And so in applying this theorem, you look at what's called the partition graph, right? So since the theorem only says things about pairs of parts which are regular and have positive density, your partition graph has a vertex for each part, and it just has an edge if that's one of the pairs where the lemma says something, where the part has positive density and is well behaved, is regular. Okay? And what this theorem lemma tells you, one thing it tells you, is that if you've got a clique of size chi of h in this for some small graph h, then you will actually also have a copy of h. Okay? Think about it if it was a random graph and you had a coloring of h and you had your clique, you could put one of the stable sets of the coloring in each part of the clique. And then if it was random, the probability that you actually got h, well, each edge is there with probably at least epsilon, so your probability is like epsilon to the number of edges of h, which is maybe small constant, but it's a constant. But the point is, this is a graph with n vertices. H is a constant size. You can do that n, you can do it at order n times. So you've got probability you fail is a constant. The probability you succeed is 1 minus that constant to the n. Right? So you almost surely get a copy of h. Okay? And the regularity lemma says that same thing is true here. Okay? If you have the clique, you'll get a copy of h. So you don't have a clique. So what does that tell you? It tells you don't have that many edges. Okay? Because I know then how many edges are in the partition graph. Well, I don't have a clique, so the best thing I can do by Turan's theorem is to have this proportion of the edges have positive density. Okay? So for the guys that have positive density, they'll have the same number of proportion of edges in G. Okay? And then what else can I get? I can get the guys that don't have positive density. Well, they've only got density epsilon, so every part, summing up over all the parts, I only get epsilon n choose 2. I can have the irregular pairs of parts, but that's only an epsilon proportion of the pairs of parts, so summing up over them, that's another epsilon n choose 2. And then I can have the edges within the parts, which is 1 over p. And that also goes to 0 because the way the lemma works is you let the number of parts go up high and then epsilon comes down. And so you get that if you have one little o of n squared more than this, you're gonna have a copy of h. So that's the proof of the theorem. Okay. And it relies on, it's not really relying on the property of h, right? It's relying on the property of dense graphs, right? So what happens with bipartite graphs? Well, bipartite graphs, the answer isn't known. Erdős showed in 65 that it's like, so this is just for cycles, not arbitrary bipartite graphs. Just to show you it's hard even for cycles, it's not known. For a cycle of length 2k, the upper bound is n to the 1 plus 1 over k, and the lower bound is n to the 1 plus 6 over 7k. And the problem still hasn't been resolved after, 60 years now. Right? So it's much harder to get a handle on what's going on with bipartite graphs. Okay? But there's one particular class of bipartite graphs where things are easier to understand.
Can I ask a question?
Yep.
Yeah, so for the lower bound, is it the random construction or the... Yeah.
I'm not really sure. Actually, I think the random. I'm not really sure, so I shouldn't say. I think it is a random construction, but I'm not 100% sure. So now I want to talk about trees, right? And I think you all know what a tree is, right? What's a tree? It's a graph you can build by taking a vertex, the root, adding an edge, guy with an edge to it, taking another guy, adding an edge in, adding an edge in. Keep adding one guy that just has one edge, right? Or if you want to think about the growing it from the root, just keeping adding a guy that's only incident to one vertex, right? Okay, and those graphs, we have a better understanding of the Turing number. Again, we know that they're within factor of 2. Okay, and let me explain that to you. Okay, first the lower bound. The lower bound, right, it says that you can get a graph with number of vertices minus 2 over n over 2 edges. And that's easy, right? I just take a copy of a clique with 1 too few vertices to put t in it. Another clique with 1 too few vertices to put t in it. Another clique with 1 too few vertices to put k in it. And how many edges am I getting, right? This one has vt minus 1 times vt minus 2 over 2 vertices. That one does 2. That one does 2. Right? Number of edges is vt minus 1 times n over 2. Or to give another example for a specific graph, a star. Right? If I have a star with t's a star, then the center of the star has vt minus 1 neighbors. Right? See all the rest of the tree. So I take any graph which is vt minus 2 regular, and I can't put that star in because I don't have a big degree vertex. Okay? So that's the lower bound. And what about the other bound, upper bound? I went the wrong way. Maybe I went the wrong way. Okay, well, we saw how to grow a tree, right? And that's how we're going to do it. Okay? And what do we need then? Every time, all we need is we need to have an empty, unused neighbor of the person we're embedding's parent. Right? He's not connected up to a whole bunch of stuff. He's connected up to one guy, and there just has to be space in that guy's neighborhood. So what do we need? That guy has to have vt minus 1 neighbors, right? So as long as we've got delta g as minimum degree, right? As long as we've got the minimum degree is vt minus 1, then we can embed. But we're talking about the number of edges, right? To answer the number of edges, which is the average degree, right? The total degree is just twice the number of edges, so the average degree is just twice the number. I mean, so how does this help us? Well, the thing is, take a minimal counterexample to this statement that the Turing number of trees is at most vt minus 2 over n. I claim that, well, I shouldn't have actually said this, but anyway, okay. Take a minimum counterexample of the statement. Does it have a vertex whose degree is at most half of the average degree? What happens if it does? Throw that vertex away. What happened to the average degree? We lost its degree, 1 from each side, and for each of its neighbors we got 1 degree. So we lost twice its degree in total, which is the average degree. And we lost a vertex, so the average degree did not go down. Right? So we keep doing this. The average degree doesn't go down, and eventually we stop. Right? And then everybody has average degree. Everybody has degree bigger than half the average. Right? So that's what I said here. In any graph, G, you can get a graph of whose minimum degree is bigger than half the average, and in particular, in a minimal counterexample, you would have that. So then you just embed in this graph. Right? It's minimum, if you have this many edges, right, then your average degree is twice that. Right? It's twice VT minus 2 because, again, your degree, total degree is twice the number of edges. So half your average degree is VT minus 2, and you've got a minimum degree bigger than that, which is VT minus 1. Okay. So here it's not about the structure of the host graph, it's about the structure of the tree that we're trying to embed, right? Because we have this just post order out a guy only adjacent to one other vertex property. We know the answer within 2. And the Erdős-Sós conjecture, which is old as I am, right, says that actually it's the lower bound that's right. So k minus 2 over 2 times n edges, or average degree bigger than k minus 2, means that you can get every tree with k nodes as a subgraph. Okay? So that's the conjecture. And there was a proof claimed for large K in the 1990s by Samarati and Simonovich, but I think it's safe to say that that proof will never be written.
Can you click the screen? Yeah.
Whoops.
Yeah, now it's okay.
And so let's think again about a minimal counterexample here. We know the minimum degree is half the average degree, bigger than half the average degree, because otherwise we just throw away a minimum degree vertex, right? I mean, we know, of course, that the maximum degree is bigger than the average degree, right? So we know that the maximum degree the maximum degree is at least k minus 1. And every vertex has it bigger than k minus 2 over 2. So it's natural to ask, is that enough? Right? Maybe you don't need anything with the average degree. Maybe all you need is a maximum degree is at least k minus 1. So you can put a star in. And that the minimum degree is at least exceeds k minus 2 over 2. Okay, and the answer to that question is no. Right? So think about G. Right, so you have 2 cliques. Okay, I don't want to use 2, sorry. Each with 2L minus 2 vertices and a vertex which sees all of them. Okay? So delta of G is 2L minus 2. And this guy, delta of G is also 4L minus 4. Right? And now think about your tree T. Being formed from 3 stars with L vertices by adding a root which sees the center of each star. Okay? So K is 3L plus 1. Right? So for large L, 4L minus 4 is bigger than 3L plus 1. So my maximum degree is as big as I'd want. And my minimum degree, it's like about 2/3 of L. So it's bigger than half. Right? So this satisfies those two properties, but I can embed this guy in here. Why? Well, if I put the root in V, then two of these guys, then each of these guys is going on one side or the other, and two of them have to go on the same side. And that's 2L vertices, and I don't have enough. Right? And if I don't put the root in V, say I put the root here, then one of the stars can intersect V, but the other two don't. And the other two are attached to the root. So they both have to stay in that side. Okay? So that's one counterexample, and I'll show you another counterexample. Same tree, slightly different graph. Okay. It's a complete bipartite graph and a vertex that sees everything. Okay? And now, if I put the root in V, then two of the stars have to go in the other side. All their roots go over here. That's 2L minus 2. And at least one vertex of the other star, because every edge has to go across. So that's too much. And if I put the root down here, then one of the stars can go over there. The other two stars' roots have to go over here. All of their leaves plus the root is on the other side. And that's too much. So that's not true. So with Have-Stein and Wood, we made the following conjecture that actually, if your degree is like 2/3, then delta k minus 1 is enough. Okay? So this is sort of the worst example. You're going to need just a little bit more than that. And Besme-Stein says, okay, if you really want to stick with the minimum to be being half of the size of the tree, then actually what you're going to need is delta being 2k instead of k. Okay? And
Are these theorems or conjecture?
these are conjectures, sorry.
Uh-huh.
Sorry, to be clear, yeah. Theorems are on the next slide. These are conjectures. And that 2k is the best bound possible. The example that shows that is kind of a combination of these two ideas. I won't show you the graph that shows that that's tight, but that is a tight conjecture. And then also they made sort of a parameterized version which says, okay, if delta is bigger, the min degree is bigger, then the max degree can be lower, right? So there's some kind of trade-off here. Starting at k minus 1 up over 2 and going up to 2k minus 2 over 3, and starting at k minus 2 and going up to 2k. Okay? And okay, now saying all the theorems. Okay, so there is a function f such that if your maximum degree is big enough, then all that you need besides that is that your minimum degree is k minus 1 over 2. Okay, this function is like quite large, but it is true that all you need is maximum degree to be sufficiently high, and then every other vertex can have degree k minus 1 over 2, and you'll be able to embed that vertex. Okay.
But here is induced subgraph?
Oh, sorry, no. So that's a mistake.
Ah.
Please delete induced.
Okay.
Thanks, Daniel.
Like complete cups.
Because we all know it's not induced subgraph, it's minor. It's minor. Okay. And now here's a theorem that Davudi Piquet Reda Sanweza Matala. I'm sure I pronounced those all wrong. Okay. So what are you saying? Minimum just a little bit better, right? So epsilon better than what we wanted, k over 2. And now, right, you don't just want one vertex a degree bigger than delta. You want to have 1 plus epsilon. You want to have a epsilon proportion of the vertices degree 1 plus epsilon k, right? And then also you need that the number of vertices is not too big, right? So you basically they want to apply the regularity lemma, which means that they need to have a dense graph, which means they can't have that many vertices because they've only got average degree k. So if you had more than order k vertices, you couldn't apply the regularity lemma. So they're only proving it for graphs which are bounded by constant times k. Then the theorem true, right? And this proves, right? This proves Erdős-Sós for dense graphs, right? If we, instead of saying k over 2 minimum degree and k maximum degree, suppose we said 1 plus epsilon k over 2 minimum degree and 1 plus epsilon k average degree. Okay? Well, if you don't have that many vertices and your degree is 1 plus epsilon k, then you got to have a fair number that actually have degree bigger than k, right? Because even if the highest degree guys had degree were universal, so everything else, that still wouldn't eat up too much of the degree. You'd still have guys that were a little bit bigger than k. Okay? So this actually says is if you replace both the lower bound and the upper bound by something that's just a little bit bigger, then the theorem's true for dense graphs, for small graphs. Okay? So that's kind of interesting because right, all we've done is imposed, we had forgotten about average degree entirely. Right? It's just the maximum degree, and well, it's not really true because, but yeah, it's just how many vertices are of degree bigger than k, and then the minimum degree condition. Okay. Okay, but you know what? This is not what we want to talk about. Because, as we all know, especially Samuel, it's minors, not subgraphs. How many of you know what a minor of a graph is? Okay. So a minor, you take a subgraph and then you contract some edges. Okay? So that means you pull them together into one vertex. Right? So you take these two vertices and you make them one vertex, and then their neighbor, the new vertex, is their union of their neighborhoods. Right? This guy sees both his neighborhood and his neighborhood, and when they have a common neighbor, you lose one of those edges. You replace the two edges by one. Right? So that's what minor of a graph is. And another way of thinking about that is, let's talk about a model of a graph. Okay? A model of a graph. So here's H. If I'd been better prepared, I would have used Korean letters. Okay. Here I have to U. I have a vertex. All right, sorry, I have a tree for each vertex. Right? They're disjoint trees. Okay, so this is in G. This is the model in G. And if there's an edge of the graph between the vertices, then I have to have an edge in G between the two trees. Okay? And I have H is a minor G if and only if I have a model of H and G. Okay? I take each tree and I can track the edges down to a subgraph, down to a vertex, and then I get H. Okay? So they're the same thing. I like models better because it tells you like where things are. Now this is the fundamental theorem of extremal graphs here. This is about minors, not about subgraphs, right? It's asking how many edges do you need, right, in a graph with n vertices, right, to have H as a minor, okay? And the answer is always linear, okay? It's always a function, a constant that depends on H times n, the number. The number of edges you need is a constant of it, depends on H times n, which means the average degree is a constant which depends on H. Okay? And essentially this theorem, I may not have exactly the same constant as matter, but essentially this theorem was proved by Mater in 1968. He showed that if your average degree was at least 2 to the I minus 1 minus 1, then you have a clique of size r as a minor, which of course means you have every graph of size r as a minor, because you can just throw away the edges. Well, your model of the clique is actually also a model of the other graphs. Just don't ignore the edges. Okay. So how do you prove this theorem? Well, a minimal counterexample of this theorem, it's not the codegree which you can bound. Sorry, it's not the degree which you can show as high. It's the codegree. It's the common neighborhood of vertices, right? Think about x, y. Here are the neighbors that both see, right? And here's private neighbors of x, private neighbors of y. Right? What happens when I contract x and y? I lose this edge, right? And I lose one of those edges, one of those two edges every time. But I don't lose any of those edges, and I don't lose any of those edges. Right? So the number of edges I've lost is just the codegree plus 1. So if the codegree is less than the average degree minus 1, then when you contract, the average degree goes up. Okay? So now in a minimal counterexample, we don't have that the average degree for here would be 2r minus 1 minus 1. Half of that. We don't have it, which more than half of that is 2 to the r minus 2 minus 1. We added the codegree is at least that. Right? And now we're done. Right? Just take any vertex V. That's going to be one vertex of the model, or tree of model. And think about its neighborhood. Right? All the guys that adjacent to it. What's going on here? What do we have here? In this graph, every vertex has degree 2 to the r minus 2 minus 1. So the average degree, bigger than the minimum degree, is at least 2 to the r minus 2 minus 1. So in the neighborhood, we can build our model of a clique of size r minus 1, and then add b, and we got a clique of size r. Okay? Beautiful theorem, right? And again, it's all about codegree. Right? And it's not a property of the graph, it's a property of the minimal counterexample. Makes sense? Okay. So, it's natural to ask, what happens if you have average degree greater than k minus 2, then you can have every tree on k nodes as a minor, right? Erdős-Sós says this, right? Because if you have a tree as a subgraph, you have it as a minor, you just use single vertices for the images of the model, or in other words, you don't do any contraction, but you still have it as a minor. So this conjecture is a weakening of the Erdős-Sós conjecture. I suggested it about at least 15 years ago to David Wood as an easy problem he could do quickly. 15 years and 150 pages later, we showed it's true. Okay, and so this, see, I put theorem there so you know. So this,
150 pages?
yeah.
Oh.
Okay. So what's the idea here? Okay, yeah, that's sorry, I want to go back. What's the idea? What's the idea? Oh, it's gone. It's gone. I mean, what do we know about trees, right? What makes them nice? Everybody only has one parent. That's right? We add one in, we add one in, we add one in. Or we grow it out, better think of it. Grow it out, grow another one, grow another one, grow another one. So if you're going to look for the model, it's natural to put this guy down and look for the next one, look for the next one, right? So it's natural to think about a rooted variant where you actually say this vertex is going to be in the image of the root, right, of the model. Okay, and so that's what this is about. And it turns out to talk about this variant, actually I don't want to do that. So this is a binder variant. What's the main difference? We're specifying a vertex and saying that it's in the image of the root, right? We're rooting the tree, we're rooting the graph at a vertex and saying root of the graph has to be in the image of the root of the tree. What are the other differences? Well, it's only going to be true for connected graphs, right? Because V could be a singleton. I could have the whole rest of the graph could be a huge clique, 2 to the k vertices. But if V is a singleton component with no edges to anybody, that don't help me, right? So we need to say connected. Okay, but that's not really a difference because if you think about the minimal counterexample to the unrooted version, it's also going to be connected. Because the densest component will have average degree as big as the average degree of the whole graph. So in a minimal counterexample, we better have that it's connected, otherwise we just reduce to the densest component. So that's not really an issue. And we're using a slightly different definition of density. So we're not dividing by the number of vertices to get the average degree. We're dividing by the number of vertices minus 1. Okay? And then we need a slightly higher condition. We don't need k minus 2 over 2. We need this density parameter to be k minus 1 over 2. Okay? And also, the theorem is actually false. The theorem is false if you only have k vertices, so we need to say k plus 1. Okay? So those are the differences. But even though we have these differences, it still turns out that from this rooted version, you can prove the unrooted version. Okay? And like I said, connected doesn't matter. K plus 1 version doesn't matter because it's really easy to prove the unrooted version when you only have k vertices. If you take a random embedding with positive probability, it'll work. You can show that. So that doesn't really matter. And then there's just a nice little argument that shows that you can derive the unrooted version from this rooted version. So we want to look at a rooted version because we like starting and building it node by node. It turns out we can specify a statement that will imply the unrooted version. But this is also sort of interesting on its own right. I'm very scared that somebody is going to find a 5-page proof of the unrooted version, but at least we'll still prove something with 150 pages. So let's think about proving it. How do you do it? Well, just go out, right, and start building your tree, right? Do the next node. You know that V has to be in the image of this guy. Now we want to do the rest of the tree. And like to keep your life easy, don't bite off more than you can chew. You may not be familiar with that expression. It's an English expression. Let you figure out what it means. Let's go down to the component which is as small as possible, right? When we're trying to build the rest of the tree, let's just start with the smallest pieces we can. So okay, I've rooted this guy here. I want to decide where to put his child. Okay? So I take the child in the tree with the fewest descendants, and I decide where to put him. So I'm going to choose the vertex in the child's image and the edge to this image, and then I may need to extend out into a path here, because it may not be V that's adjacent to this guy in the image, it may be something else in the path. And then I would contract that down to a vertex. So I figure out where this edge is going, contract down this piece, and then I've got that one. Okay? And if, as in this example, if we embed a leaf, then we're good to go. We can do this contraction. We throw that away. We've gotten the leaf. He's only got one edge. And then we say, okay, if we did this properly, we have the conditions to prove that we can embed the rest of the tree in what's left. Okay? I mean, we have to show that we can do that, but that would be our approach. Try and choose something to contract and a vertex to put this in delete so that the conditions hold so that we can embed the rest of the tree. Okay? And then, another easy example, right, is if there's only one child. Okay? If there's only one child, we do the same thing. We decide where this edge goes. Sorry, this is the root. This is V. We again may need to add an edge in here, or add a path in here that we're going to contract in, because that edge goes there. And then we put this guy here, and we contract that in. And now we can delete the root, because we're done with it. There's no more edges out of the root. So now we're doing this tree, and again we hope that we've got the conditions right so that we can apply the theorem to embed that tree. Okay? But then, the next thing is that we may choose, okay, which one of these trees has fewer vertices? This one, right? We don't have a root. We got two guys, so we choose a smaller one. We choose this guy to go here. We choose what to contract to get to the edge to there. We contract that. We put this here. But now we can't throw anything away. Right? We still need stuff out of the root. And we still need stuff out of this guy. So we need to keep them both. So we have to form about rooted forests. Okay? So instead of talking about rooted forest trees, we're going to talk about rooted forests. Bunch of trees, big disjoint trees. And what's nice about them, the smallest one has size 2. Okay, because if we've only got one vertex, we're done. And also, everyone is bigger than all the rest. Right? Because when I did this, I chose the smallest component. So I split it into 2 trees. Right? But this one is less than that one. Because this one is at most the same size as that, and I got one more vertex here. And then when I go now to the smallest tree and do it again, this one will be less than that one, and their union will be less than that one, because I won't have touched it, and so on. So I do have to prove it for forests, but fortunately I only have to prove it for ballooning forests. Okay? So here's the theorem. I got a forest of roots, it's ballooning. Biggest one is size at least 2. Every guy is bigger than the sum of the smaller ones. I got a graph G. I've decided on one vertex that's going to go in the image of each root. And I want to say if certain conditions hold, there's a model of F and G where the ith root is in the image of the root of the ith tree. Right? And then it's got to be true for some set of conditions. I can say if the minor exists, it's right. But what are the conditions that we need here? Well, one obvious thing is we need connectivity. Right? Like with a rooted tree, you needed the graph to be connected because otherwise all of the density could be in another component. Right? Well, here you need the density connected to the whole root set. Right? So a bad cut is a set of vertices which has less than our vertices, fewer vertices in the roots. And if I look at some component here, when I throw it away, okay, so the number of edges incident to this guy is more than the average, is more than A of G times K. So if I were to throw it away, right, then what's in the rest of the graph, I don't have high enough density maybe, and I maybe can't reach here because this cut set prevents me from using it for the trees. Okay? So this is the connectivity condition that we have to impose for the general theorem, which doesn't hurt us for a rooted tree theorem because we already said connected, and that wasn't a problem. Right? When you only got one root, you're just saying it's connected because x has to have size 0. Okay, so we have this connectivity condition, so that's one thing that we have to deal with. And the other thing we have to deal with, this is not true. Okay? Theorem you would think might be true is not true if you just put in the connectivity condition. And here's a counterexample, okay? Think about these two trees. So forest has 8 vertices, tree of size 3 and a tree of size 5. It's ballooning, right? 5 is bigger than 3. Right? And here's your graph G. Okay? It's got a clique on 4 vertices, including the 2 roots. And it's got a stable set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17 vertices. That's relief. Each of which sees all 4 vertices of A, but B is a stable set. Okay? So, we got 8 vertices. In the tree, we got 21 vertices. Whoop. In G, how many edges do we have? We have 4 times 17 plus 6 in the clique. That's 68 plus 6, that's 74. And K minus what? Oh, did I do that wrong? I did do that. Well, I should be dividing by AG minus 1. Okay, don't notice, please. Anyway, this is almost the right counterexample. I actually probably got a couple of vertices to be. So the density is bigger than 3.5 times the number of vertices. Right? The number of edges is bigger. No, I think that's okay, actually. Yeah, the number of edges is bigger than K is 8, right? F is the number of K is 8, the size of the tree. K minus 1 is 7. K minus 1 over 2 is 3.5. I want 3.5 times 20 vertices, which is 70. Edges, I've got 74. So I got the density I need. And there's obviously no cut set of size less than K because this is a clique of size, or size R. This is a clique of size R, and everybody's kept all of it. So there's no 3 cut in this graph. So I got a connectivity condition. But the tree doesn't exist. And why don't the trees exist? Wait, did I do this or not? No. The trees don't exist because think about ripping off these 2 vertices. Okay? And in the trees, I've still got this edge, and this edge. I'm matching a size 3. 3 disjoint edges. Okay? And the image of an edge, okay, has to have an edge in it. Right? It's got that image, the edge between the 2 image guys is an edge. So where are those edges going to be? All of them have to use a vertex of A. But there's 3 edges and there's only 2 vertices of A left. So you can't embed it. Okay? And so more general counterexample, you have 2M paths, 2M paths, right? And each path is an odd tree and they're ballooning, they're getting bigger. Right? B is a stable set. A, right, is exactly half the sizes of the tree. Okay? And B is much, much bigger than A. Okay? So because B is bigger than A, our density is going to be bigger than K minus 1 over 2 because each guy in B sees K over 2 vertices. All right? So the average degree of those guys is K over 2, and as they go to infinity while A stays the same size, the average degree of the whole thing goes to K over 2, which is bigger than K minus 1 over 2. So this is going to be a counterexample. The same problem is going to arise. Throw away the 2 vertices, right? I'm still going to need a stable set, right? That is of size half of the trees over 2 minus 1, and they all have to use vertices in here, and there just aren't enough vertices. Exactly the same problem. Okay, I think I'll keep going because it's not hard to show that. More general counterexample in the same way. So now we define a special minor. Okay, so it's a graph. It's got R roots, V1 prime to V prime R. So there's a model of J and G, right? And it takes the root of G, ith root of G to the ith root of J, and the density in J is at least as big as the density of G, and there exists a set of vertices of the root such that when you rip it out, you don't have a matching of size k minus s over 2, which you might need because the rest of the tree might have a matching, and that would have to have this many vertices. Okay? So, this is what a special minor is, and again, I don't think I have time to show you, but it's not hard to show that you can't have one when you've only got one root. Okay? Exercise. Okay, now here I can tell you the theorem. If I got a bunch of trees, I got a ballooning forest, I got the graph of G with the specified roots, I got the density condition, I got the connectivity condition, then either I've got a rooted special minor, right? Or I get the model of the forest I want. That's the theorem. 53 minutes for the statement, 3 for the proof. That's a theorem. And like I say, it applies the theorem for trees because you don't have special minors when you only got one root. So this condition drops out, and you don't have bad cuts because it's connected, and so you get the tree. Okay. So let me very briefly give you an idea of the proof. 2 minutes. Okay. So the pre-processing, we want to get the codegree high, right? I mean, that was nice. Made Mater's theorem trivial. So we like to contract an edge until the average degree is at least, or sorry, until every codegree is at least half the average degree. Okay? What's the problem? We could lose a connectivity condition, right? We had these no bad cuts. Well, we could have a cut that's a size R instead of less than R. When we contract an edge, now we have a cut of size R, and it's bad. Okay. And also, we could reduce, we had this condition that you had to have more vertices in the number of trees, and we could reduce down to the number of vertices in the tree. Right? So you wouldn't have the conditions of the theorem anymore. So how do we deal with that? Well, you prove the case for k plus 1. You prove the base case as always. Right? You prove the base case separately. Right? And then you prove there's no near bad cuts. Right? So you prove that there's nothing that could contract down to a bad cut. You need to make an argument about that, which I'm not going to explain why. I wish I had time, but I won't. Okay? And then now you've got this nice average degree condition, which is sweet. Now, right, we do exactly what, I mean, I've shown you what the reduction step is. Right? You want to contract in a little bit and add this vertex and do the reduction either, and you might possibly add a new tree. Okay? So what are the problems with this, right? Well, you need to prove that after you do this, the conditions of the theorem hold for what's smaller. Right? Because you need to prove the average degree is still big enough. You need to prove that there's no bad cuts and so on. Right? You can't just arbitrarily choose where to embed this bit. And how do you deal with that? Well, it turns out that you need to do a few more reductions. There's slightly more complicated reductions. And then you need to prove that if you can't do any of these reductions, it's because you got really high degree in the neighborhood, and then actually you can put the tree in there. Then there's about four different proofs like that. Okay. And then the last thing is you have to go back from the solution to the reduced problem. You have to say, okay, I've got the solution to the reduced problem. That gives me a solution to the original problem. Okay? And that's not hard if the solution to the reduced problem is an embedding of the reduced forest, because that's exactly how you define the reduced problem, so that if you got a solution for the reduced forest, you would have a solution to the reduced problem. The problem is you might get a special minor for the reduced problem, and then you have to show that you either have a special minor or an embedding of the forest for the original problem. Okay? Turns out if a special minor contains basically the thing you saw, A, B, all edges between A and B, you can almost embed. You're just missing a little bit there. Just missing a few vertices, and then it turns out that you can take that into G, and again you'll be able to embed. Anyway, that's enough, I think, about that. So can we determine the density condition Sherman F for every rooted forest, right? So I've only been talking about ballooning forests, but you can ask this question about arbitrary rooted forests. What's the density to get a rooted minor? And again, you need to put in the connectivity condition. Is there, and I sure the hell hope not, is there a short proof of the minor variant of the Erdős-Sós conjecture? I hope not, but I suspect yes. Okay.
Why would you hope not?
147 pages for nothing?
Thank you. Any questions? So if you increase the average degree a little bit further, can you
Yeah.
can you have some?
Yeah, you can
other-
drop the special minor condition if you say it's k plus r minus 2 over 2. So just a little bit higher. Because r is like log k, right? The trees are going down by a factor of 2 every time. So the number of trees is most of the log of the number of vertices in the forest. So instead of k over 2, you need k plus log k.
Yeah, so do you expect to have some matroid analog? Because the ratio that you have is A of G is this number of elements divided by rank of the.
I've seen how to approach this. That's a very good question, Sego.
Okay.
One that I will not be able to answer. Maybe, I don't know. Sure, think about it.
Any other questions?
What if the host graph is regular? Is that easy to find the?
Yeah, because then host graph is regular, then your minimum degree is also is bigger than your average degree, so then you're just greedily. Your minimum degree will be k minus 1 over 2. Okay, and I showed you how to do that. Yeah.
Do you think a similar statement is true if you, instead of considering minors, you have topological minors or subdivisions?
No.
Okay.
No, for the simple reason. Oh, wait a sec. Yeah, no. The simple reason being that you may put the root may have high degree, and you put the image of the root in a low degree vertex. Okay, that's the simplest example, but there are other similar problems, right? So that's why it can't hold unless you say minor. Thanks for the question.
If we aim for like outer planar graphs, or then do you think it's
Well,
like 3 with 2 graphs, or?
I mean, I think it's more interesting to think about for Erdős-Sós, right? To think about proving special cases of the sub. I mean, I know I shouldn't say subgraph, but especially yeah.
Is it possible that after you do this contraction so that you have the code read condition, that you get it as a subgraph?
My guess is no. And sort of like because of counterexamples for the subgraph thing, I think you may have to pick up stuff in more than one place, and there's a cut. My guess is no because of packing, like this one third versus a half problem. But I don't know.
All right. Any other questions? So, if not, let's take the.